Okay, so thank you all for being here. This is the second special session, and this special session is going to focus on network on chip security. Okay, so security today, I think it goes without saying, is becoming an increasingly important design concern. We are all aware of the traditional attacks on software and security related to that, but more and more we are also now seeing attacks on hardware. Right, so there's been studies that have shown recently that there have been backdoors, hardware Trojans integrated into electronic chips designed for controlling weapons and nuclear plants and so on. And so this is obviously an important challenge, right? And so we've heard about attacks at the core level. We've heard about hopefully things like Spectre and Meltdown. You may have also heard about attacks on memory architectures, things like Rowhammer type of attacks. And in this community, we know that networks are the glue that combine all of those components together. So as increasingly in the global supply chain, we get our network on chip components from third parties, these network on chip fabrics are also susceptible to hardware Trojans and potentially security attacks, right? So the goal here in this special session is to talk a little bit about some of these challenges at the NOC level. And the unique aspect of this special session is we want to look at the evolution of NOCs and look at how we have a lot of these challenges that sort of go beyond a technology, a single technology. And so we want to talk about when we look at different types of network on chips from a technological perspective, we're looking at electronic, we're looking at wireless and photonic NOCs. What are the security challenges there? How do they manifest? And what are the ways that we can address some of these challenges? So with that, I want to move on. And so this special session has 3 talks, where the first talk is going to talk about and cover electronic NOCs and security challenges in those sort of systems. The second talk is going to focus on wireless NOCs and security challenges in those sort of platforms. And the last talk is going to focus on security challenges in photonic NOCs. So without further ado, let's get started. And so let me first introduce John, our first speaker. So I'm going to stop sharing, and John, you can start sharing your screen. All right, so while he's loading up his slides, John, let me just say a few words about John. John Jose is an associate professor in the Department of Computer Science and Engineering at IIT Guwahati. He completed his PhD from IIT Madras in the field of computer architecture. He's the recipient of the prestigious Qualcomm Faculty Award in India in 2021. He also serves as the vice chair of the IEEE India Council, and his research group in multi-core architecture in the Systems Lab at IIT Guwahati explores various challenges relating to the domain of networks on chip, cache management, non-volatile memories, hardware security, and domain-specific accelerators. So, John, go ahead.
Thank you, Sudeep. I hope I am audible and my slides are there.
Yes.
Okay. Okay. So once again, thank you, Sudeep, for the introduction. As he has already mentioned, the series of 3 talks would be talking about security aspect of electronic NOC first, followed by wireless, and followed by the optical NOCs. So what I'm going to talk for the next 10 minutes is about hardware Trojan management approaches in electronic NOC-based SOCs. So this is going to be the brief outline. I will first introduce you about tiled chip multi-core processors. I'm sure that over the last 1.5 days, you all will be hearing about various types of introduction to NOC. So for the NOC route, there is not much introduction required about NOC. I will then introduce you about the possibilities of how hardware Trojan enter into the NOC circuits. And then we take a very few number of cases of how Trojans can attack. And especially my focus would be on how packet headers are being attacked and what are the potential consequences of such attacks. And then we'll deal about one such case of how to mitigate with these attacks by detecting the Trojan, localizing it, and the corresponding mitigation mechanism. And then I will further conclude. So as we all know that the utility or scientific applications and handheld computing devices are part and parcel of our day-to-day life. And we all start our day with some of these apps and end our day also with some of these apps. And these are running on powerful computer-driven or microprocessor-driven tablets or handheld devices. But ultimately, at the end of this, these are all being powered by powerful multi-core processors. So whether it is going to be a smart home or a drone application or a cell phone or an autonomous cars, our future of all these important gadgets are going to be driven by multi-core processors, that what you see there. And in this multi-core processors, let's try to see what is inside that. So this diagram will show you like what is inside your processing element. So here I am just trying to introduce you about tiled chip multi-core processors, where we have row-wise and column-wise organized tiles. We integrate multiple cores on a single tile, and then it is interconnected via packet-based network. So we can see that the zoomed version of the tile, which involves processor, multiple levels of caches, instruction and data cache, a network adapter, and a tile controller. And these are connected together with the help of a network on chip. So here we are going to deal about the electronic NOC, the conventional one which first started. And what you can see there, the internal architecture consisting of input ports, which is known also virtual channel buffers. And then there is essentially a crossbar which connects the input to the output. And the whole movement of packets is being controlled by various control units like routing unit, virtual channel allocator, and switch allocator. All these are very much familiar term for the NOC crowd. So we do have to understand that this NOC is going to connect various of your cores with the help of the underlying switching network, and typically communication between memory hierarchy is been passing through this. So we need to service these packets, which are essentially cache misses or request or reply packets, as soon as possible to reduce the underlying average miss penalty. So if you look at the basic functions of an NOC router, it involves buffering of the flits, and then for every head flit, you do the route computation, virtual channel allocation, which is essentially reserving your buffer in the downstream router, followed by switch allocation, traversing the switch, and at the end, we have the link traversal. So for flow control perspective, packets in network on chip are split into smaller units known as splits, which consists of a head flit, one or more body flits, and a tail flit, which ends the sequence. And we typically follow a wormhole routing for this approach, and head flit typically contains the control feeds like what it has been shown here. It has a process ID, source address, destination address, its packet length, the type of the packet, the priority, any other commands, and typically it carries the memory address which need to be fetched or written to the next level. And the body or tail fits generally contain the payload field. So in order to connect the corresponding head flit and the body and tail flits, we need to have some kind of a mechanism which is called a common prefix, what is being shown in the green box on the left side, where FT stands for the flit type, and the VCID will contains the address of the next downstream buffer, so that the body flits also can reside in the same place. Now, if you look at the communication NOC, consider the case that you have a 16-core tiled chip multi-core processor with a 4 GB memory and a total 1 megabyte of shared L2 cache with a 64-byte cache blocks. So imagine that we are following a policy of a private L1 cache and a shared distributed L2 cache hierarchy. Consider the case that you encountered an L1 cache miss. So I need to bring the data from the corresponding L2 tile, for which I need to travel through the interconnect. And how will I know what is my destination tile? So based upon the L2 cache specification that is being given, conventionally we know that the physical address is split into tag, index, and offset. And then here the calculation will show you that you have 2 power 14 sets. And out of the 14 bits used for set index, the first 4 bits we used for the tile number, and the remaining 10 bits will point out to one among the 1024 sets. So if you split this address, you can see that this 4 bits, it's been marked in the red color, which point to 0101, that is tile number 5. So essentially the packet, let's say it has been given here, the source of S that is being given, and then from the source S, where you encounter an L1 cache miss, and since tile number 5 is the destination, so a packet need to start, a request packet, cache miss request packet need to start from the source tile, traversing through the network, and it has to reach the destination tile, which is marked in the red color. So we follow the XY routing, that is a traditionally simple and standard routing with a wormhole switching and credit-based flow control and reply packet generation that also happens. Since these terminologies are very much familiar to the NOC community, I'm not going deeper into it. So we follow an XY routing. So a request packet will start from the source router, travel in XY path, and it reaches the corresponding destination tile, from which the L2 cache block is being brought as a sequence of head fleet and followed by body fleets. So this is the role that is being played by the underlying the interconnect. So what you carry is the cache miss request packet, write back packets and all. So when you look into the security challenges associated with NOC, if there is any security vulnerability, it is these kind of crucial packets that have been triggered by a memory operation from the core that the NOC is carrying. So how do we get security vulnerability challenges? We all know that long and globally distributed supply chain of hardware IPs will essentially force the SOC designers to make use of third-party IPs, and which can lead to vulnerability at the trust and integrity issues. And so this vulnerability can be at the specification level, or it can be at the design integration level due to designer mistakes or due to rogue employees. It can happen at the synthesis level due to EDA tool vulnerabilities, or through an untrusted vendor, or lastly at the fabrication level also due to an untrusted foundry. Due to rigid time to market constraints and the cost constraints, many of the vendors are forced to release their chips at a very short span of time, considering the competition that they face. And this can lead to such kind of security vulnerabilities by making your design exposed to various third parties. Let me now introduce the concept of hardware Trojan. Hardware Trojan is basically a malicious circuit inserted in an IC that can alter the system behavior to produce an undesirable consequences. So consider the case that you have a normal input, and the normal circuit for a given input, it is going to give some output. But when you have a hardware Trojan, and if it is triggered, it is going to give an altered output. So you can have hardware Trojan. There is possibility of a hardware Trojan in any portion of the NOC. So it may malfunction. If it is in the routing circuit, it may give a totally different routing output, or if it is in the credit-based system, then it will give a wrong credit output. So these things can lead to havoc. So here I would like to introduce to hardware Trojans, which are manipulating the packet headers. I will introduce you to two hardware Trojans. The first one is manipulating the destination ID field of the head fleet. And the second one is going to manipulate the fleet type field of the common prefix, which stitches together the head and body for facilitating the wormhole routing. So this NOC internal structure of the router is being very familiar to you. So consider the case that this is the zoomed version of your one virtual channel, where whenever a packet comes, the corresponding output port is finalized and it will fill in the OP. And the corresponding VC ID has been identified by performing virtual channel allocation. And depending on there is a packet length, which will tell you how many more body fleets are going to come, and the status field, which will indicate whether this particular virtual channel is free or not. So the first threat model that we consider is when an HT is present in one of the input buffer of the virtual channels, and the HT modifies packet destination ID to a random destination ID. And we assume that there is only one HT that is present at a time in this network, and we can further extend later also. So for making the concept understand. Now let us try to illustrate what happens. Consider a 4x4 mesh NOC, where you have a packet that is starting from source tile 4, destined to tile 15, and assume that there is a Trojan that exists in router number 5. Let's say this is the packet. What is marked 1111 is the destination address. At 5, the destination address 15 is randomly changed to 3. So the packet will move further. At the 6 and 7, the routing will happen as if the destination is 3, and eventually the packet will not move to 15, and it will eventually reach 3. We can look that in the head fleet, the DID field is 3, and there is an address field that corresponds. And in my initial illustration, I have shown that at the address of the destination tile is also a few bits of the physical address. So at the node 3, you will perform a comparison check whether this particular request is meant for it or not. The address that is extracted from the address field, the tile number, will not match with the destination ID, and this packet is being discarded. So what happened is, it may be a cache miss request packet looking for the corresponding block to be fetched from 15, and that particular reply will never come. So 4 is going to time out, and it is going to create trouble. So you are going to request for a packet, and the packet will never come. And in the NOC setup, since we assume it is like a lossless network, there is no retransmission mechanism. So then eventually your reorder buffer, which holds the outgoing request, and the MSHR will never get a reply back, and that leading to application level stalling. So we use the standard the Gem5 simulator to model this with appropriate cache and the network parameters. And then what was very interesting to know that we are just trying to talk about 4 scenarios: the NHT, that is called the no HT scenario, the normal network, and HT, which is shown in blue bar, where there is one HT that is present, and in this case, randomly it was being chosen as router number 5 when HT is present. And then we have just modeled the 2 scenarios where we assume that we have a retransmission circuit, the yellow bar and the green bar, with a different retransmission timer interval. Even though such a kind of system is practically not there, we were trying to see what if there is a retransmission that is there, and if the retransmitted packet successfully reach destination. So what you see on the left-hand side bar is basically about at what time the reorder buffer was last updated. So the lower the blue bar, it shows that the reorder buffer update happened very early when compared to the total length of the bar. We can see that in core number 5, the reorder buffer update happened until the end of the execution window. So wherever the reorder, where the blue bar is small, it shows that the execution stopped there because the reorder buffer became full and no more issue happened, and as a result, IPC drops. So you can find a correlation on the right side for each of these core numbers. Wherever there is a reorder buffer that got full very early, you can see that there is a drastic reduction in IPC. We can see that in core number, the packets moving from core number 0, it got some kind of a DID impact in core number 5, and accordingly, they never came back, and there was the reorder buffer getting full, leading to further block of the issue. So the IPC values dip significantly, except in core number 5, where HT is present, and some of the cores like 11 and 12, they may not have any packets that is being moving. So similarly, we conducted different kind of spec benchmarks also we used, considering from workload 1 consisting of all high MPK benchmarks to different combination of high and low. We took only 4 different benchmarks, and then across the benchmark, we can see that the solid bar indicates on the top graph, the solid bar indicates the IPC values, the average IPC values, where the red one is no HT and the blue one is with HT. So there is a drastic reduction in IPC. And when you use a retransmission circuit, then the IPC values are picking up. So we also computed average miss penalty, which is yet another architectural metric that is very much required to know the performance of an application. Your miss penalty increases when HT is enabled, and when you do the retransmission, it is slightly coming down. So what we conclude is when there is a minor Trojan which will change the destination ID field, it can create havoc in IPC level and miss penalty level. We tried with a different attack probability of the Trojan, how frequently the Trojan is going to attack with various probabilities. As probability increases from 0.05 to 0.15, we can see that the IPC values are degrading and average miss penalty values are increasing. So now let me bring your attention to another Trojan, where we are now focusing on the flit type field. So in the flit type field, what we do is we have a 2-bit which indicates whether it's head, body, or tail. And the flipping of these bits will make a head as body and the body as a head. And this will block the further movement. So if a head flit become body flit, no other head flit based operation like routing, virtual channel control, these things were not done. And accordingly, things were be moving. So coming to the illustration, like you have a packet that is moving from 4 to 15, it's supposed to. At 6, it got modified to a body flit. And since it is a body flit, no other movement is there. And accordingly, the remaining flits, that is, the body flits, will get stuck. And we call it as dead flits. And that will create a congestion-like scenario in the nearby places. Here also, we tried with various benchmarks and then by varying write intensity. And we can see that when you have no HT, that is a green one. And HT that changed from head to body, that is known as blue, and body to head, that is known as the red one. We can see that IPC drastically reduces and the average miss penalty significantly increases. So what is the solution when you come to look forward is, the simplest one is, can somebody identify, can a genuine router identify, let's say 4 identify that 5 is going to be a Trojan, and there is a gray point kind of a mechanism, it will pass on this information to the neighbors. So if many such neighbors experiences the same scenario, there is some kind of an anomaly that is being detected. And then we can form a cage. And once the cage is erected, then no more packets will be moving through the HT router. So that's a basic idea that is been using. So packets that is coming from the outside will not move into router number 5. And for this to happen, all the routers have to come to some kind of consensus. A quick flash through how we can detect. We come up with a new module as part of the NOC router called Delomi module, which consists of a detection, a dynamic caging unit, and a rerouting unit. And what we use is we try to stick on to the integrity and authenticity of packet at every router you need to check. The conventional hashing and digital signature algorithm, which is to be customized to NOC, is used using Pearson's hash, which is well suitable for NOC, and asymmetric encryption is used using the Elgamal digital signature customized for the NOC. So essentially, we need to have a key manager, a key generator, and a hash generator and a hash verifier. Each sender will compute the hash, digitally signs it by its private key, and store the signature. At every packet, you need to spend some extra time to recompute the hash and figure it out how it is. So more details should be available in the paper. In the interest of time, so whenever 27 detects that something wrong coming in packet coming from 28, it will send some special alert flicks. Similarly, if 20 also detect the same thing, it will send special alert flicks to neighbor. And once if multiple router converges on it, then we are going to erect a cage. So once the cage is erected, then there is a rerouting that has to happen. So a packet which was supposed to move from S2 to D2 will not move through 27, rather it take a rerouting. Similarly, a packet from 54, which is conventionally moving in this path to D1, it will also be taking an alternative route like this in order to reach this. So experimental results clearly shows that across different types of benchmarks and combination, it shows that with this mechanism, we are able to significantly improve the performance. And in handling dead flicks, we are checking the cumulative buffer occupancy of packets and anomalous packets count. And accordingly, based upon that, we find that certain regions there is of high activity, high buffering. And we found that using our security mechanism, the average miss penalty was able to regain back. And more details should be available in the paper. So the conclusion is packet header attacks by hardware Trojan in NOC and its impacts. We have modeled it. Lightweight cryptographic and hash-based solution will be helpful in dealing these attacks. And the qualitative analysis of the impact of HT at the core and cache level is being studied. And we have proposed a few real-time mitigation technique by fleet flow analysis and encryption methods. So the future work revolves around building a cost-effective HT mitigation technique. And this work has taken some of its inputs from some of our previous works in these publications. And thanks to all my team members who worked in different portions of this work, and work is still continuing. And with that, I conclude. I'll be open to take some questions. Thanks.
Thank you, John. Do we have any quick questions at this time? If not, so I would propose perhaps keeping some time at the end of the session for questions. In the interest of time, let's move on to the next speaker. So the next speaker is Sujay Dev. Sujay, you can start sharing your screen. He's an associate professor in electronics and communication engineering at the Indraprastha Institute of Information Technology, Delhi. He received his PhD from Washington State University in 2012. He's the recipient of the DST Inspire Faculty Award and is currently serving as the IEEE CAS CSS Delhi Section Vice Chair. And his research interests are in the broad areas of power and performance efficient and reliable NOC architectures, heterogeneous architectures, hardware for deep learning, and low-cost biosensors for healthcare. So go ahead, Sujay.
Thanks, Sudeep, for the nice introduction. And thanks, John, for making life really easy, because you have already introduced the vulnerabilities which primarily are of concern for the network on chip in general. So here I'll be focusing on wireless network on chip and the basically challenges associated with it. It's primarily the security related challenges. And I would like to acknowledge here the group members of my team in the Advanced Multi-Core System Lab, and specifically Siddharth Shankar Raut. He's a PhD student, and I'm primarily going to present his work. All right. So I'll very quickly try to motivate why wireless, because it's not very intuitive that why somebody would like to put wireless interconnect in a chip. So as we are all familiar with the regular stored program model, where bus is the interconnection mechanism, but soon with the more number of cores, this bus becomes a bottleneck, and when we are talking about thousands of cores, we need something better than bus, and that's where the NOC comes in. And we are all in this community are familiar with the advantages of NOC, the modular nature, the scalability, etc. But if we look at, as John also highlighted, how the request and response is dealt in a wired NOC, you will see that the communication is primarily multi-hop. So if a processing element 1 wants to communicate with processing element 16, so it will has to go through these multiple hops, and as your NOC becomes larger and larger, this number of hops becomes a bottleneck, and also basically it consumes significant amount of your energy. Almost a huge chunk of basically cheap energy is consumed by the NOC itself. Now, to address this issue, there has been different approaches. People have looked at regular topologies with long-range links, basically introduced on top of the regular network to form some kind of a small world network. Now, the advantage of small world network is that the overall average hop count comes down. Your many of the overheads related to multi-hop communication can be addressed. Now, how do you implement those long-range links? To implement them efficiently, if we go with traditional interconnects like copper wires, etc., there it becomes very difficult, specifically because of the long wire related issues. We are very much familiar with the fact that as we scale things, our global wires don't scale that well. So to address that, people have tried many different ways of implementing futuristic interconnects, like optical, which Sudeep will be talking about, waveguides, and we also looked into wireless. Now, the advantage of wireless is that you can basically do not have to lay out any interconnect, but you can't put too many wireless because of their overheads as well, because there you need to build transceivers, you need to build antennas which will be communicating at a particular frequency. So you have to be selective, like where you want to put those wireless interfaces and how you want to utilize them. So let's say we in this hypothetical 4x4 network, we put these 4 wireless interfaces, and the same communication scenario we are looking at. So P1 wants to communicate to P16. Now the communication can happen like this. So you go to the nearest wireless hub, and then from the nearest wireless hub, you go to the destination. So this looks really promising. The other advantages of wireless is that like you do not have to have physical layout, and you can dynamically basically establish connection between different wireless interfaces. For example, in this case, we saw basically P2, which has a wireless interconnect communicating to P12. But similarly, if they are working in the same frequency range, then this wireless interface can communicate with this wireless interface as well, whenever it is required. So these are the advantages, and why we want to introduce, or you want to have the same channel for communicating among the wireless links, because establishing or building these wireless interfaces is non-trivial. Now, if you want to introduce multiple channels there, it becomes even more difficult. And wireless bandwidth is also a cause of concern. So you want to optimally use your wireless resources. That is, and that's why, like, you can't compete in all aspects with, let's say, optical counterpart using the millimeter wave wireless links. Now, as John has already highlighted the security vulnerabilities in case of electrical NOC, on top of those vulnerabilities, because you are still talking about an electrical NOC and it is augmented with wireless interconnects. You have more vulnerabilities here because now you are introducing a shared medium of wireless channel, which you will be using for long range communication. Now, since this is a shared medium, you need to have some kind of access mechanism, media access mechanism. So typically the way this access mechanism work is basically if you go for simplest kind of channel access mechanism like token passing kind of approach, then you equally share the time basically when each of these channel will get their turn to send messages. But because this we are building NOCs for basically sophisticated applications, so not necessarily all these wireless interfaces need to have equal amount of share of basically transmission time. If you have heterogeneity in your network, then you have to intelligently figure out like who should get how much share. And a hardware Trojan at any point can again create havoc by changing that. So I'll explain it how. So let's say in this scenario, we figured out that okay, we will have a distributed mechanism. Okay, so we will have a distributed mechanism to figure out which wireless interface will get how much time. To do that, we will observe how much load is there in each of these channels, and accordingly some either basically in a simplest manner we can keep a central table where we will keep this information, and accordingly we will give this time for each of these wireless interfaces to send their messages. Now this table can be altered, or basically this table has some input about, let's say, this amount of time this let's say H3 will get to send their messages. Now when it is supposed to get reset that timer, the Trojan might alter that. So that kind of vulnerability we can have. Similarly, the other vulnerability could be where you play with the header fleet itself, as John has pointed out, that if some Trojan plays with the header fleet, then in that case there will be like spoofing kind of attack where your messages will be going everywhere without going to the actual destination. So the security issues are highlighted here, basically reiterated here. So the channel access mechanism can be malfunctioned by some hardware Trojan, where basically the wireless interfaces will get affected. Rogue third-party intellectual property codes can also can change the headers, etc. Yeah, so the techniques are manipulate the channel hold time or disturb the channel access arbitration pattern itself. So instead of going in a particular sequence, you change the sequence and so on. So this can result to denial of service kind of attacks or spoofing kind of attacks. And ultimately, the impact will be underutilization of your scarce resource, which is wireless channel. And it can also lead to starvation of your healthy WIs, healthy wireless interfaces. So I'll briefly introduce how this can be illustrated. So a simplest approach could be a centralized controller, but in general, centralized controllers can introduce more vulnerability. So if we look at a distributed controller where each of the wireless interfaces actually, by sharing information among themselves, they figure out the ranking of which wireless interface will get how much time, and according to that they get the access and basically how much time it will be able to hold the channel, etc. So in these kind of scenarios, the basically the threat model could be like this. So we it can be denial of service. So denial of service can happen by this simple let's say timer based Trojan, which, let's say this is the access time register, and if it can manipulate the load enable to this access time register and puts arbitrary values whenever this access time register is getting to its reset value, then one particular wireless channel will infinitely hold their channel, resulting in denial of service for the other wireless interfaces and basically underutilization of the wireless resources. So to prevent that, what we did, we proposed this modification in the in our router, wireless router itself, where we have this distributed ranking based channel access controller. Now, what is this distributed ranking based channel access controller? So it has, based on the shared information from everyone, the access time for each of the channels or each of the wireless interfaces. So this is a table which gets periodically updated, and whenever this time gets this time expires and still the next WI or wireless interface does not get the token to basically transmit its messages, then it raises a flag. And that also is basically supported by other wireless interfaces, saying that, okay, this is not a random observation. All other wireless interfaces are also observing the similar kind of observation. So some kind of a majority voting is done, and based on that, a security flag is generated. Similarly, for a spoofing kind of thing, for example, if the headers are getting manipulated, in that case, the wireless interfaces will not get their fair share of turn. And if that happens, then again, that flag will be generated. And again, majority vote, with majority vote technique, we will figure out there is a problem. And we will isolate that particular wireless interface with the Trojan in it. So with this, we found that we could actually increase the utilization of our wireless interfaces. Of course, because we are basically in an attack scenario, the performance of our wireless utilization will go down, and that's what is shown in the with the red bar. And with our reconfigured system, of course, it will not be as good as the without any problem system. And we see that on an average, we could improve 45% of wireless utilization, and it also led to network throughput as expected. So to conclude, we see that because of the shared nature of the wireless channel, it is inherently prone to attack, apart from the other electrical vulnerabilities. And also, and to prevent that, our work proposes a threat model and countermeasure for the, so that this can be handled. And because of PVT and other variations, basically overall this wireless channels are pretty vulnerable to this kind of security measures. And there are, I think, there are a lot of open questions which need to be answered before we actually can claim to have a secure wireless network on chip available. So I think there are a lot of interesting research directions that can be explored from here. So with this, I'll conclude, and I'll thank all of you for your time and attention. Thank you.
Thank you, Sujay. Do we have any quick questions from the audience? If not, we can just keep the questions till the end. So feel free to type them out at any time in the chat window, or we can sort of open up the floor at the end. All right, so I think we can move on to the last talk. So let me go ahead and share my screen.
Yeah, and I'll just take this brief moment to introduce Sudeep. So for all the audience, Sudeep Parsicha is a professor and director of the Embedded and High Performance and Intelligent Computing Laboratory at Colorado State University. He received his PhD from the University of California, Irvine in 2008. His research interests are broadly in the areas of algorithms and architectures for embedded system, mobile computing, and high-performance computing. Professor Parsicha has extensive background on the design and optimization of NOCs over the past 2 decades. So over to you, Sudeep.
Thank you, Sujay, for the nice introduction, and hopefully you can see my screen.
Yes.
Okay, perfect. All right, so thanks. So today I'm going to be talking about security in NOCs from the perspective of photonic NOCs. And so again, I'm going to try to not repeat a lot of things that perhaps the audience in this very special symposium knows about, but just to kind of make sure we're on the same page. If you think about the costs today of accessing data from, for example, DRAM, we're talking about approximately picojoules per bit, which may seem pretty small, but it's not as small anymore, given how much data we need for our applications. If you think about the overheads in terms of moving data, that's where the biggest bottlenecks crop up. And so if you think about moving data across chiplets, for example, across high bandwidth memory and cores and so on, we're talking about 10 times as much energy per bit. And if you think about moving data across chips, we're talking about 10 times more compared to the previous number, right? So clearly, data movement is a big challenge today. And so what I believe, based on the research that we've done, is that photonics can have a big impact. So photonics here can be a panacea for overcoming a lot of these data movement bottlenecks. So over the past decade and a half, in my research lab, with the help of several of my PhD students and also undergraduate students who did really all of the work, as well as my collaborators, we've been designing different PNOC architectures that essentially combine optical links together with electrical links. And so we've pioneered the use of different techniques for example, partitioning traffic across photonic and electronic networks. We've designed new types of architectures that combine different configurations for optical links. We've pioneered and pushed for serialization at gateway interfaces, by bandwidth steering in a dynamic manner. We've also designed 3D architectures, free space optics architectures, and then also more recently, architectures designed to accelerate workloads for big data and machine learning. In fact, most recently, we've also been looking at the design of architectures and protocols for photonic networks at the 2.5D level. So this work, which will appear, and we'll present this in a few weeks at ICCAD. And this work's done by, actually in collaboration with Madhi Nikdast, our co-chair of NOCS. And here we propose an architecture that sort of scales across chiplets and intelligently connects these chiplets. So beyond the architecture level, there's also been quite a bit of work. In our lab, we've been focusing on this goal of high bandwidth density, low energy per bit for photonic NOCs. And while architecture level research is absolutely critical, we also need to look at other levels. So we've been doing quite a bit of cross-layer design, and we've been looking at devices, circuits, doing things like modeling and analyzing crosstalk across different wavelengths of light and within the same wavelength of light. We've looked at thermal optimization. At the chip level, these optical components are quite sensitive to temperature variation. So how could we manage this, the correct operation of these devices in the presence of hotspots and gradients in temperature? We've looked at how to optimize power at the laser level. We've also looked at optimizing power for tuning. And then also we've looked at various aspects of modeling reliability and ensuring error-free communication in these networks. Now, just to very quickly introduce the basic components that I'll be talking about. So what I've shown here is just a very basic microring resonator device, this loop device, and a waveguide, which essentially is made out of CMOS compatible material. So you can actually fabricate a lot of these optical components in CMOS compatible conditions in the same fabs that we today fabricate our electronic chips. And here, for example, with silicon dioxide, we can achieve total internal reflection so that we can actually confine wavelengths of light, and we can actually confine them to structures that we design that are part of our photonic NOC architectures. So ultimately, what we want to do is we want to send digital data over this optical link, which is basically sending data over light. And the way that this happens is you need to use some sort of optical device, and you need to use some modulation mechanism. So here, what I'm talking about is using this microring resonator device, which takes in this bit stream, and you can actually have this bit stream imprinted onto wavelengths of light. So for example, this red-colored microring resonator is working with the red-colored wavelength that's tuned for it. And this on-off keying modulation, that's one of the techniques that you can use. It's fairly straightforward. If you want to send a 1, just let the red wavelength pass through. And if you want to send a 0, just absorb the red wavelength, right? So at the destination, what's going to happen is you can have another of these sort of MR devices that couples out the light and drops it onto a photodetector. Then you can pass it through some sort of an amplifier, and then you can use analog to digital conversion to retrieve your digital bit stream. So in a nutshell, this is how in an optical link, we use microring resonators devices for this optoelectric conversion process. Now, in an optical link inside a photonic NOC, we have potentially multiple wavelengths, and we make use of something called wavelength division multiplexing. Here we are essentially using multiple wavelengths in parallel. We can have tens of these wavelengths where we send multiple bit streams in parallel and multiple MR devices to do the sort of things that I showed you in the previous slide. We can also use other mechanisms here to enhance bandwidth density. For example, mode division multiplexing is another approach, but I'm going to restrict this discussion just to WDM for now. Okay, so let's talk about security in these photonic NOC architectures. So what I've shown here is just a very, very high-level overview of a photonic waveguide-based architecture that's coupled to a very lightweight electrical network. Turns out that just like John and Sujay talked about the electrical and wireless networks being susceptible to security challenges, you can also have hardware Trojans embedded into these sort of hybrid photonic NOC substrates. So you can actually have cores that are running software, essentially malicious programs that interface with these hardware Trojans that could be implemented in the routers. And in this case, the GI is the gateway interface between the optical and the electrical domain. And that is one place where you could potentially have hardware Trojans. There could be other places as well. So these hardware Trojans in photonic networks on chip can launch various types of attacks. It could be data integrity attacks, data confidentiality attacks, or availability or denial of service type of attacks. So here's a demonstration of what these sort of attacks look like. I'm going to start by talking about data confidentiality attacks. So what I've shown here is just a simple waveguide part of a photonic NOC. And we have potentially multiple MRs in banks of MRs. And so what you can have is multiple of these banks corresponding to different gateway interfaces along the waveguide in your photonic NOC. And the way that things work here is, again, aligned with what I mentioned earlier. If you're using on-off keying, your MR could be in a sort of a passive state where it just lets the light pass. It could be in the active state, actively tuned to or not, but it can essentially absorb the light from the waveguide. Or it could be in a sort of a partially detuned state, where it absorbs only part of the light signal and it lets the remaining part of the light signal go. And the reason we make use of this sort of an approach, this sort of a mechanism, is to support broadcasting in optical links. So if we can actually partially detune multiple MRs, we can actually allow the light to send the same information to multiple receivers. And so this is a very useful ability to have in any sort of a link. And this is what is done in buses, electrical buses. And this is also what we want to support in our optical links. Unfortunately, if we support this, we create some problems. And the problems are that this sort of a partial detuning approach can be used by malicious nodes. For example, the one that I've shown here, this malicious node could actually snoop some information from wavelengths that it's not supposed to, and because of perhaps hardware trojans embedded into its interface. And this can create data confidentiality concerns. We may have snooping concerns, and this is a serious concern in photonic NOCs. So to overcome this, what we have done is we've looked at this problem for over the last several years, and we proposed this Soteria framework that first identified these problems for the first time at the chip scale level in optical links and optical networks. And then we proposed this cross-layer framework for photonic NOC security enhancement. This is a cross-layer framework because we propose optimization techniques at different layers of the design stack. In particular, we're looking at a technique at the circuit level and a technique at the architecture level. So let me talk about very briefly about these techniques. So at the circuit level, in order to ensure data confidentiality, perhaps the most classical thing you can do is to use some sort of encryption. But if you use some of the conventional encryption techniques, they're quite heavy in terms of their overheads. So our goal was to design very lightweight, but yet quite strong and unique encryption techniques that are difficult to crack. And so the way that we approached it is we looked at the domain of optical devices and their properties in order to help formulate our encryption protocol. And the way that we did it is, so we came up with this encryption technique that uses encryption using codes, where the codes are derived as a function of the drift of the microring resonator devices, which is a function in itself of the fabrication process variations on the chip. So the idea here is that every chip will have a slightly different fabrication process variation profile. The devices will have some aberrations, slight aberrations that are different across chips, even though you're imprinting the same circuit on them. And if we can measure this drift in the microring resonators because of the fabrication deformities in these devices, we can actually capture that as a signature, a unique signature of the devices associated with each receiver at inside each chip. So we use that information to create codes, or in other words, keys, to encrypt and decrypt information. So every receiver has this unique key as a function of its microring resonator bank. It's stored in a lookup table, a sort of a read-only memory, and every sender has access to those keys for the receivers that it communicates with. And so the sender node, essentially with these keys, can essentially just XOR their data with that unique key. And then the receiving node, by just XORing that same information, when it receives it, can decrypt that information. So it's a very lightweight approach, and it's also a strong approach in the sense that it, even if an attacker can get access to keys on one chip, those keys will be different on another chip. So you can't really very easily hack different chips if one chip gets compromised. So this sort of an approach is interesting. It works within the parameters of the problem to some extent. However, it's also possible that your hacker can actually decode the snoop data if it gets access to these keys, these codes in the ROM, and if it knows what the destination of that information is, right? And so both of these pieces of information are needed in order to get that information, right? So in order to understand this problem, it's important to see how exactly things are organized in today's PNOC architecture. So in general, in almost every photonic NOC architecture, we have some sort of schedule for sending information to synchronize the sending. You usually have a reservation cycle slot where you indicate who is the receiver of this information and where is the source. And then you have the data slot where the actual data transmission happens. So in a data waveguide, it could be a single writer, multiple reader, or multiple writer, multiple reader type of a waveguide where you have multiple detector nodes. You will need this sort of a reservation selection mechanism. And what this involves is to essentially have a wavelength be sent and the detector node essentially would have one wavelength associated with it that allows it to identify that it is the recipient of the data in the next cycle. And the other interfaces can then perhaps power gate and turn off so that they can save energy. And so in the next slot, the data cycle slot, you actually then send the data. Now, if you actually have a malicious node snooping information, it can snoop this wavelength selection and or detector selection by snooping that wavelength associated with the detector. And now it has information about the receiver, and it also has information. If it has information about codes, it can now decrypt and actually snoop the data successfully. So to prevent that process, what we came up with is an approach at the architecture level where we changed the design of the optical architecture slightly, where we added this sub waveguide link, where essentially we decouple the process of the receiver selection with the data transmission, where here, what we are doing is we have a dedicated microring resonator that is tuned to only a particular wavelength. This could very well be a passive device, doesn't have to be actively tuned. And so now we essentially, in the reservation cycle slot, we couple the wavelengths and send them to this separate segment of the waveguide. We use double microring resonators here. These are used because these double MRs have some nice properties compared to single MRs. They prevent the light from essentially recoupling back into the waveguide and creating interference and homodyne crosstalk. And also from a loss perspective, there are some desirable aspects here. But the interesting thing about decoupling in this way is that it's very easy to see if this particular circuit at the detector with the one single MR has been manipulated. So a malicious node perhaps would make this an active node by adding a tuning circuit or add another microring resonator. These things can be easily detected. And without doing them, however, a receiver cannot know who the destination of the next data transfer is. So in doing this sort of a manipulation of the architecture and changing it this way, we are able to, again, make the architecture a little bit more robust to attacks where the keys have been compromised and the receiver information is potentially susceptible to be known. All right, so quickly, some results. So we tested out and we looked at the application of this framework on several different photonic network on chip architectures. I'm going to show you just results for two of them, Firefly and FlexiShare, although we've looked at other architectures too. We looked at detailed architecture level simulation with different applications. Before I show you results, one other thing I want to tell you is that in these photonic links, one very important thing that happens is loss. Since light is traveling not in free space, it's actually traveling through some medium. It's not at exactly at the speed of light in vacuum. So you will have some losses in the signal. And whenever you have a bend or just because of the length of the waveguide, you can actually have losses in the signal. So these losses actually increase when we implement what we did in our Soteria framework. We actually end up adding more microring resonators or changing the length of the waveguide. So this is an important thing to note as I show you the results, right? So this is the result for the worst case signal power loss for the two architectures. So the first bar really shows the baseline architecture. And then the second one shows what happens after we add the Soteria framework, right? So you can see there's a slight increase in loss. That's because of the additional components we add. But this increase is quite small. And so really, these architectures with Soteria are much more secure, but there is a cost that we have to pay. And in this case, it's in terms of the loss. The loss, essentially, to compensate for it, we need to increase the laser power. So ultimately, it becomes a power overhead, a slight power overhead. And we've captured that in our energy delay product, also looking at performance. And again, here you see that there's a slight increase in EDP because of making the architecture a little bit more secure. It costs a little bit. And so there are these quantified overheads that we discussed, but these overheads in general are small. They're also architecture specific. So some architectures, the overhead is much smaller. So that's actually an interesting insight that some architectures are easier to secure than others in a more sort of practical way. Okay, so the other attacks that are possible are potentially data corruption, which is a data integrity attack, or a denial of service or availability attack. How do we handle those in photonic NOCs? So quickly, just to give you an insight here. So we did some work, and this is work from our DAC paper in 2019, where we came up with these lightweight detection circuits that can help us isolate malicious nodes. So we had these very lightweight circuits sitting at the interfaces of the networks, where we used aging information of these circuits. And surprisingly, you can find out some really interesting insights even over short durations of time. And that can help us identify nodes that are part of denial of service attacks, or nodes that are snooping information or corrupting information. And so we also came up with lightweight key-based approaches to help with that. And then lastly, over the last few years, we've also been looking at machine learning-based anomaly detectors. And so we proposed several of these detectors for embedded and IoT platforms. These can be used for detecting corruption and denial of service attacks. However, we have to ensure that they are lightweight for chip-level integration. So that's something it's an open problem. We're looking at it. And there's quite a bit of work that needs to be done. But interestingly, this is not a gratuitous use of machine learning. We actually showed that these approaches outperform statistical and well-known other anomaly detection techniques that are the state of the art and don't use machine learning. All right, so to wrap up, I talked about today how photonic NOCs are susceptible to various types of snooping, corruption, and availability attacks. This is certainly an open area of research. So if anybody is looking for new areas of research, this is absolutely a very nice area to work on. I talked a little bit about one of the frameworks that we proposed. It's a cross-layer framework that looks at circuit and architecture level security enhancements that helps you with data confidentiality attack detection and mitigation with fairly minimal overheads. And then I also talked about the potential of using some lightweight detection techniques and machine learning-based anomaly detectors that can also help us with data corruption and denial of service type of attacks. All right, so that's it. Thank you so much for listening to my talk. Again, acknowledgements to all of the many students who have helped with this work, my collaborators, including Madi, who I enjoy working with. We work on many interesting problems together in the domain of photonic networks and photonic interconnects and photonic computing. So I'm open to questions at this time. Thank you.
Well, thank you, Sudip. I think there's a question in the chat box. I think this is related to the prior talk. It says, what is the future of wireless in NOC? Any products?
So I don't think there is any product yet on wireless NOC. The uniqueness of wireless NOCs are basically quite interesting. For example, the flexibility it provides to establish links dynamically. These are very unique, and I think instead of if we are looking at only high bandwidth data communication, wireless may not be the right choice or may not be able to compete with optical. But for other control signal passing, or rather different kind of housekeeping signals, I think wireless could be a very important or very good choice. And going forward, like I think with 5G and 6G, this transceiver design and the related challenges will be much more mitigated. And yeah, I think it does hold some interesting promises, especially also chiplet based designs can get a lot of advantage from wireless interconnects.
Yeah, thank you, Sujay. Any other questions from the audience? You can always raise your hand. Oh, there's, I think, one more question. Oh, I think the person who asked the question just thanked you. Other questions from the audience? You can also raise your hand if you have any questions, or type it in. I think while that is happening, I have a general question. So thank you. I think we learned a lot about security concerns in 3 different emerging platforms, including the conventional platform for NOCs. My general question is this: so if we have a hybrid network, when we have like optics and then wireless in it, and of course we have the electronic links, Does it mean that we have to now be concerned about all of these possible security concerns, or somehow the combination of these different technologies are going to help make the system more secure? I know this is a very general question, but I'm just wondering, I'm just curious to know your idea about, if we combine everything, is it going to get worse, or, there's hope to get things a little bit better?
So, John and Sudhir, you want me to take this? Do you mind if I take this? Yeah, okay. All right, so thanks, Madhi. Yeah, this is a very important question. I think, firstly, it's creating heterogeneous network architectures like the one that you propose, where all three technologies are used, is somewhat, well, it's going to be an interesting use case if we ever end up with that. But nonetheless, use cases where we have at least two of these technologies being used is fairly, I think it's going to happen. Now, what can we do there? Well, I think the most important thing to note is that the techniques to detect the attacks and then the techniques to mitigate these attacks can operate at different levels. We can have these techniques working at sort of an architecture and protocol level, where if the same sort of protocol is reused across technologies, then we can actually leverage the same technique across technologies. However, I think as you may have seen across the three talks, there are also very specific technology implementation specific approaches where the attacks are enabled because of a specific component being used that is very specific to the technology, like a wireless transceiver or an optical microring resonator, right? So there, obviously, we need to make sure that we understand the unique attack surface that is created with the use of these different types of devices. And so then we have to obviously make sure that there are mechanisms to deal with the unique technology-specific attack vectors.
Yeah, thank you. That makes sense. One quick question before we start the panel discussion. This is from the audience again. It says, many research now focus on chiplets. Which one would be better for chiplet interconnection? Wired, wireless, or photonic? All
right, so you want us to fight now in 2 minutes and resolve it?
Not me, it's the question. And I think if you could make the answer short, I would appreciate it.
Yeah, sure. So we only have 1 or 2 minutes. So Sujay, John, you want to take a crack at it? Any thoughts? Which is better? Well, let me go ahead, Sujay.
Yeah, please go ahead.
Well, I was just going to say, in the interest of time, this is a very nice question. It's a very open question too, right? So it's really difficult to come up with a definitive answer because technology moves quite rapidly. And what we were able to do 10 years ago with wireless or photonics is very different from what we are able to do today. Same with electronic NOCs, right? So it's hard to predict what's going to happen 3-4 years down the line and which one of these technologies is going to really be clearly the winner. What we know is obviously the momentum is all behind electrical NOCs, but since we are achieving a point where there's bottlenecks at the interconnect level, there's a lot of interest in looking at optics and wireless communication mechanisms, right? So open question and great question if somebody wants to do a thesis and compare these and maybe fabricate them and compare them. And then we have an answer.
Yeah, thank you so much. Well, I appreciate it. I think this was a really interesting special session. Thank you, all three of you. I think I can see Rado in the participants. So yeah, I think we can take maybe like a 2-minute quick break, and I guess we can then start our interesting panel after that. Thank you.